Okay. So in the previous lecture, Rakin talked about some of the aspects of string theory, uh, but I'm not quite sure if string theory characters solve a lot of problems related to actual physics or cosmology. Like I worked on the cosmology for a long time now, but there's but I mean, as soon as it seems like string theory is very nice when it's a supersymmetric theory because string theory is inherently supersymmetric. Uh, and the ball on the top today is so that you know when offshore or subrat they come, you guys can understand what problem they are working on, right? So also for is the also the issue we're just going to talk about like black hole information paradox and how you can solve some of the black hole problems using string. So just to give you a little flavor, so let me write a black hole metric, which is this. Um, yeah. So this is a metric for a black hole, right? And you know that at r equals to 0, we have a singularity, right? And the metric I wrote is a black hole anti-density space. Okay. So the canvas diagram for a black hole in anti-density space is kind of like this. Okay. So this r equals to 0 part, right? I don't know how to highlight this part. Um, this is the singularity, right? And r equals to infinity, there is a boundary. Okay. Now we know that the black hole, this black hole has an entropy, right? Like if you compute the area uh, that is enclosed by the horizon. So this is the horizon basically. This line is basically the horizon, right? And and the area of the black hole is given by basically some power of this, depending on the dimension of the black hole. So the question is if the black hole has an area, and we know that the entropy of the black hole is given by the area law, right? Like the entropy of the black hole is given by a formula, um, something like this. Ready? So the question is, what are the microstates that is associated with this entropy? Because we know that whenever there's entropy, right, there should be some microstates that describes the number possible states. Because what is entropy? You remember how statistical mechanics works? That entropy is like you can have allowed any states, how many ways you can actually distribute the system, right? So you have classical particle, you have quantum particles. The states are distinguishable, indistinguishable. But for those systems, we know about what compute the entropy. But on the black hole, it says that if it has an area, then we don't know how this entropy is actually earth. What are the microstates that is actually associated with this array? So Ashok Sen and many other people back in the 90s, they found out that string theory is not actually just a theory of a spin. It has some hydrogen object inside it, which are called T-break. Okay. So the purpose of my talk is actually to show that how these day breaks actually arise, so that you understand how string theory is using as day breaks solved some of the aspects of the depot information pattern. But again, the problem is those problems were solved for supersymmetric black holes. The black holes we observe in the universe are not supersymmetric. So there is an open problem to understand the black holes in de Sitter space. So these black holes in de Sitter space, the black holes we know, yeah, I can live in a de Sitter space instead of an anti-de Sitter space. But the problem is the black holes in de Sitter space, we don't know about to count the appropriate system. Yeah. But for area space, black holes in area space, we know how to count it using how to count the microstates using this techniques very developed in the 90s. So the purpose of my talk, the wrapping will be to make sure that we kind of know the ingredients of superstrings. So I will try to go there slowly, just using usual quantum field theory and some quantum mechanics tools. Okay. So one of the motivations for studying string theory is that it actually helps us to understand how to count the microstates of the black hole. But again, those black holes are supersymmetric and in the anti-resident space. We don't think in anti-resident space, our universe is definitely not supersymmetric. So we don't know how to handle these real world blackholes. Okay. And the other problem, other invariant pairs, we showed Spurgeon and Quebec, right? So they actually try to do cosmology using string theory. And one of the hot topics started when I started my PhD is this. So this thing called decimal space is it's kind of very interesting. So in the static patch, it is given by like this is right. Now you can see that again, just like this equation. How did you know that this this solution has a horizon? You know it by solving this, right? Maybe you have seen it in your GR course, right? You can solve it. And for example, when uh, when you banish this term, basically RB is given by so basically you have a real RB solution. Right? You can solve this f of R equals to 0, and you get a out where the horizon is, right? But we have a singularity here, right? But in this solution, the solution I wrote here, we don't have a singularity here. But this is a solution to effort non-negation, which is accelerating. This is an accelerating solution, right? So we know that our universe at this planet moment we are accelerating, right? So maybe digital space is a candidate for accelerating universe. Okay, but the problem is, uh, we don't know that if digital solution can be right from a space. So it's an open problem, and I think we have a very long debate, and because many people have their own view. But as far as I know, digital space, we don't know if it's a solution question. And Chipotle and Tevedo, these people are trying to understand if one can invent digital like solutions instantly, right? Cool. So I will now I have now motivated you like one of the big topics in the lecture. One is microset counting against straight to it, right? The other problem is in digital solution in the solution instantly. Okay. So you should try to understand this space a bit. I just give you something, okay? Like I draw the Penrose diagram for digital space. So in digital space, these are equals to 0. These are the poles, and this is stripe plus. Sorry. Stripe feature infinity plus infinity. Okay, and this also has an area, also has a entropy. It's called Gibbons fucking entropy. So one of the research that I try to do is to understand, because this entropy you can measure, you can see in DNA and things, but if this is a solution actually exists, then we need to understand how this entropy can be counted using the microseconds. Okay, and so people are trying to figure it out, and we have a lot of open questions relating that. All right. So okay. So in the last lecture, Raking talked about a bit about the actions of slavery, right? So let us start from there. And we know that the point particle action is given by right. So this is the point particle action, right? And this lambda is one line parameter, right? So what lambda is a one line parameter, and basically if you take any lambda, those two lambdas for tilde, we have a reparametrization through variates, right? Right. If you take lambda to lambda tilde, then we can see the action is invariant, right? So lambda tilde tells us that if there's a symmetry, uh, under which the action is invariant, then there could become comfortable, right? But the thing is, in this case, lambda is not a physical parameter. Okay, lambda is just a one-line parameter. So when you have a reparameterization symmetry like this is basically a gauge symmetry. So remember that. So we have here, we are supposed to have d degrees of freedom there, right? Because they're like index from 0, 1 to 3 to d minus 1, right? But actually, because of this reparameterization symmetry, this is a gauge symmetry. And whenever there is a gauge symmetry, you have to fix the gauge, because gauge symmetry is not a real symmetry, it's a fake symmetry. Okay. So you have to fix the gauge, and this is not a real symmetry, and we have to fix this symmetry. For example, you can choose lambda equals to x naught equals to t. Then the action actually becomes something like this. Or in other words, something like this. Okay. So here, this action, this action is a Lorentz symmetry, right? But this one doesn't have any Lorentz symmetry anymore, because you choose a gauge which broke the Lorentz symmetry. The upshot is that all the degrees of freedom of this action is not real. On the other hand, here actually there is d minus 1 degrees of freedom. So basically, d minus 1 degree of freedom is associated with the action. So if there is a massive particle, okay, moving as a point particle in d-dimensional geometry, the number of actual degrees of freedom is d minus 1. Okay, and the other way you can actually see is if you actually compute the momentum of these guys, and then you have something like this. That we can actually show this, right? So this p mu, not all of these degrees of freedom are real or actual, because there's a constraint like this, right? So basically, this actually says that d minus 1 degrees of freedom with actual. So here we actually talked about a massive particle moving in the wall in like a d-dimensional geometry. You can also do it with a mass particle, and in that case, I'm not doing that right now. In that case, that you'll have d minus 2 degrees of freedom is physical. Okay. So, but for example, if you are in four-dimensional space, and you take photon, photon has two negative thing, right? The reason I mention it to you right now is because whenever you also have string action, it also has similar kind of setup, and it also has manipulability and symmetry. So you have to be very careful when you actually count the degrees of freedom in using string action. Okay. Cool. So just to remind you something else is that if you have a Lagrangian like this in quantum field theory, which I think you guys had taken a look. So do you know what is the number operator associated with a laboratory like this? How do you write a number operator? Anybody? Right. Yeah, very good. So the number operator here is on A dagger. Cool. So this is a number operator, right? So the thing is, given a Lagrangian like this or action like this, you can always consider the number operator. So Rakesh, in the last lecture, tried to talk about the Oliaga action here, right? And it will also quantize it and create a number operator like this, right? And using that thing, now we will try to see what are the components that we have in a string theory. Okay, so just to give you a recount, what will happen is that you see that whenever you create this number operator in string theory and then act on a string backward, you will see that there was some scalar particle that will obviously pop up. Okay, and then there will be your anti-symmetric in that will pop up. But beside these scalars, something amazing will happen. You will see a graviton will pop up. Okay. So so beside these scalar particles, you have gravity in a very nice form, in a quantized form, which was one of the biggest challenge in the physics. But I'm not sure if that graviton corresponds to the universe that we live in. So there's a comment. But just for a starter, I will now show you that whatever component you will have in a string theory, right? Before this. And you will see that graviton or gravity needs it. Anybody have any question for now? No? Uh so so when there's a nestless, there is a so this action will obviously not work. This action that I wrote here will obviously not work if it's restless, right? Because A is going to be 0. So there is a formalism called, I don't know how to pronounce it nicely. Pile Pine, German name, whatever. Uh, but I don't know how to pronounce it yet. Anyway, so you have to use that formalism to make N as a come as like a parameter in your action. So here, like that, you have to see the common whatever. So in using that formalism, you can see that that for lattice particles, they're like another constraint beside this one. Okay. And using that, you can actually show that uh like it has d minus 2 degrees of freedom. Good. Cool. Okay. So let's go on. Right. So previously when we had this thing, then wall line theory. So what was it? So it was just some particle moving in space and time, right? And we were parameterizing this guy using this wall line too. So what is actually happening in string queuing? Like, what are we doing? So string is nothing, but like basically this paper you can consider as string. It's nothing also on the net. So basically you will have something like this, okay? But you can also identify this point and this point, and yeah, then you will have something like this, right? So, or in other words, you have this paper, you follow and identify it, okay? Like this. So this is a closed string, and this is a open string. Let's see. So first you will talk about closed string, because when you condense closed string, then the gravity should come. Okay. So let's see. Uh okay. So this is the boundary condition for a closed string. Cool. And basically, whenever you open a string theory book, uh, there are two chapters basically. You will obviously see one is a wall sheet theory, and the other is okay. So we call this guy for some reason target space. All right. Um, but once again, this sigma and tau are the like parameters in your spin wall sheet. Before, lambda was the wall line parameter. Now, sigma and tau are your wall shape parameter. But again, this this sigma and tau is just used to label some movement of string in the space time. So this is the parameter. So whenever you use it, you have to be very careful because of the gauge symmetry associated or rate parameter symmetry associated. So Rakin kind of showed that this is sorry. So basically, right now we are considering a string movie in a black metric background. Okay. So we are considering a black metric and a string is just moving on it. And we can see that you can take sigma. So this is a reparameterization symmetry that I was talking about. Okay. Uh, and this is nothing but the gaze here. So the problem with the number board, so this is called, I think I can told you, number go to action. So this number go to action is a bit difficult to tell it because it has a deck inside it. So whenever you want to deal, whenever you want to make uh, this guy not flash anymore, but Gnu, okay? It's like in strings movie arbitrary graph space. There, this action is a bit difficult to get. Yeah. So there we cannot use this action for various reasons. But we have another one which is called Polyakov. So this one is a bit more easier to deal with. And unfortunately, I won't be able to show how to quantize it very appropriately, but I will just make some remarks, okay? For example, it again has Lie parameterization symmetry. It also has pointer symmetry, but it has some extra symmetry, which is you can make G mu nu go as omega square sigma, not G mu nu. Right. So maybe I should mention this thing, like in string theory books, you will see that this index mu, okay, is used for identifying the space time, and these alpha betas are used to identify the string wall sheet. So basically, alpha beta runs from 0, 1, and mu nu runs from 0 to d minus 1. Okay.
Now, the pointer symmetry you're talking about is just that G.
Yeah, like Tibor mentioned, yes, he's absolutely right. The pointer symmetry is also there when J is theta, right? Otherwise, so for example, we don't know if we can quantize it in a decider background. Okay. But in the edit decider background, you can do it. But let's not go there right now. But because you have this symmetry, using this symmetry and making G mu nu as eta mu nu, the action that I wrote something like this. I must say that I am very used to the blackboard. It's very difficult for me to write on the tab. So sorry for that. Yeah. Anyway, so now if you from here you can actually compute the equation of motion, and this is nothing but space. Okay. But because we already choose this thing here, T mu nu equals theta mu nu, we have some constraint, and that constraint will be like uh, guy is 0. So you have two sets of equation. One is x dot comma spine equals to 0. And the other one is dot square plus spine square is 0. Where x dot is del x del C1 spine del. I think this is also the case. So if T alpha alpha, if the trace is 0 in flat space, that means, you multiply it with a flat metric, then T alpha beta is also 0. Long story short is that you have basically the equal. Okay. Now, I will not go into too much detail into how to solve it. You can find it in the book. But I just want to point out here that whenever there was a scalar field, this was the number operator, right? And you act with the number operator on 0 to create a state with a label k, right? Similarly, whenever you have strings and you have solution like this, then in that case, the number operators are given by so this is the number operator for us. Okay. Now just to let you know that Tiprobai was talking about Weyl symmetry, which is also, of course, very important. So whenever a string you have a string theory, you will see that the Walsh-Ricks symmetry, this Weyl symmetry, is preserved in case of bosonic string only in 26 dimensions. Okay, I will. Yeah.
So I usually said that the invisible sensor before variance. But you have an equation that it control that it should be conserved. So that's very urgent. So but if you choose the like this is optimal. So spy that counts and again alpha say what what e what. So these two sets of conditions. So when you move from the Navier action to periodical action,
Yeah.
you solve for the x's
That's his first query. And then you saw the metric is dynamic, G alpha B. The variation of the metric gives you the second query, the T alpha beta is.
Right.
That's where you get it. And you're right about that. So conformal invariance forces the rating Wendell tensor my space.
Sorry, I jumped a bit. Oh. Now I have to also jump a bit again, because I was telling you about like this wild invariance of this wild invariance thing, this thing. Okay, so whenever you have just bosonic string, you can see this wild invariance condition is only satisfied at or the conformal symmetry is only satisfied when d is equals to 26. Okay, so mu this is from 0 to d minus 1, right? So whenever d equals to 26, this is only when the while invariance is satisfied. Okay, but whenever you are moving in, you are taking like supersymmetric strings, the while invariance is preserved only when d equals to 10. And sorry. So the while invariance is only preserved um, when d equals to 10. And that means, like I say, when you have a massless spectrum in d dimension, the physical degrees of freedoms are d minus 2. So in case of supersymmetric string, the little group is going to be d minus 2, and that is 10 minus 2 equals 8. Okay. So basically, you have to study the direct product of representation of these guys. So basically, it's going to be SO8 times SO8. And to study the spectrum, you have to study this direct product of these guys. Cool. So whenever you have SO8, the vector representation is given by something like this. I'll be very quick and dirty about it, so sorry about it. And for fermions, you have something like this. So the non-chiral fermions have even number of plus or minus. And the chiral fermion yeah. And then so, yes. So what you can do is do B, 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 or F, right? So when you are dealing with these type 2 strings or any kind of string theory, this is always going to be here. So this gives you a bosonic. So let's try to compute this thing. Okay. So this guy, is called Ramon. So any kind of string theory you will want to understand, the bosonic sector of that string theory, we always have these three things with them. One is a metric, which is J mu. The other thing is we'll have an antisymmetric Bayes, okay, and a dilator. All right. So any type 2 strings will always have this. Now you will hear this thing called type 2B or type 2A. This actually depends upon this. Like, are you taking chiral fermion or non-chiral fermions? But to recap, like this guy is the number operator, right? And you are acting on the vacuum state of the string theory with this number operator. And in that case, this G mu nu, this B mu nu, and dilaton, these fields will come as the spectrum of your string theory. All right. And these things are always there in any kind of string theory. So basically, eh, eh, these are like forms, right? So in the right hand here, they enter the two forms. You have to write a lability of a two form if you want to understand the action of that string theory. So that action consider the two form, the symmetric GA and the zero form, which is pi. Yeah, there. Right. Yes. Okay. So yeah, yeah, I just wanted to show very quickly and very roughly like whatever quantity you have in string theory. But you are absolutely correct that this pi, this dilaton, doesn't have any mass, okay, and it doesn't have any potential too. So the fixing the value of dilaton in your string is a difficult job, and this dilaton has actually appeared like this. So this is the string coupling. So basically, you also explained that some gravitational field, some black oscillations. You want to get some black oscillations against inquiry. You have to make sure your phi, the value of the kiloton, takes a finite value. And this is one of the difficult job of doing stringing. So really getting some down to this phi is something non-trivial. Okay. In the next thing, I will pick the non-chiral fermion. So we will again have this guy, but instead of this, we'll have F. Sorry. Then you will have ah ah ah. Cool. So whenever we take harmonic string, although I never showed you about the polynomial function for the harmonic string, of course, separated, and then create the spatialization operator of the action, and again activate the number operator of the spatialization operator on the string that more, and then you see that your string query will then contain these higher column fields in your effective action. Okay. So beside this graviton, b mu nu, and dilatos, if you take only the chiral part of the quadratic string, you will always have this two form, this zero form, and this it's a 4 form. So why bosonic spectrum is fixed. The fermionic spectrum of hierarchy of fermionic. So this thing called chirality, I don't know how much you guys know about it, but fermionic step ion selective, and that's all now it's symmetric, and some fermions have chirality and some fermions are non-chiral. So depending upon that, the spectrum of your string theory will have the chiral field. So what will happen if you actually take a vector and a right, like this guy. We took this guy. Now we are taking this guy. So we are again taking a vector which fermion, which is non-chiral. In that case, you'll see you have this So in that case, if you take this vector plus f, then you have this right-Schindler operators or right-Schindler field in the action of field sinking. And what is super interesting is that you see when we took fermions cross fermions, all the fields that we have are bosonic, and then these are just higher form fields. And whenever you take vector plus fermions, then you actually have fermionic field in your sphinculi. And basically these fermionic fields are supersymmetric partner of your these higher form fields and this graviton and B mu nu. Okay. And I will so the type cube is sphinculi is this, that you have vector cross vector, fermion cross fermion, and vector cross fermion. And you have G mu nu, B mu nu, and phi. And you also have C0, C2, and C4. And finally, you have the Rarida-Singer fields in your spectrum. Okay. So the funny thing about string theory is that it is kind of fixed. Like the action is fixed. The action will have nothing but these things in the action. So if you can write the action just using his fields, that's your supersymmetric or supergravity Lagrange. Okay. So this is the activity action, and here you have this fermion cross fermion. The point is they are non-chiral, right? Cool. And now the type 2 string theory, you will again have this vector cross vector, which is the same as here. Okay, the G mu nu, the B mu nu, and the dilaton, they will be the same. But now you have to compute this. The F cross F, this you take as chiral fundamental. And whenever you have chiral partner representation, you have odd number of minus R or plus R. So you see here, the form fields that coming, the higher form field, are odd number of C1 and C3. So C1, C3, you see they are odd. Here, In the type 2b case, it was the even ones, right? Cool. And then you have half, 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 minus half. So once again, you see the chiral fermion cross the vector, gives you the Rarica finger field, but chiral fermion times chiral fermion, they gives you this higher form field, and this will appear in the low energy of your king fluid. So you see, this is a spectrum of flow type 2 FE. Okay. So you see that the string here, the spectrum is fixed by the Bayesian learning relation operator you before, and it fixes with the SO8 times SO8 symmetry, the rate of road symmetry. It fixes the point is that you spectrum that you have in the string. And although it seems that the type 2A theory and this type 2B theory looks very different, because you see that they have C0, C2, and C4, which are even, and here C1 and C3, they are odd. Actually, secretly, this type 2 theory and this type 2B theory are dual to each other using T duality. So, unfortunately, I will not have time to talk about the T duality, and since many of the people are already lost, so I will now stop here and let you ask some questions if you have them.